All right, so last review on simple harmonic motion. Again, we're going back to like talking about springs and pendulums because those are kind of the two big pieces of simple harmonic motion. But if we're talking about simple harmonic motion, um, or we're talking about springs first, I want to address when you use forces with springs and when you use energy. And the answer comes down pretty simply. If it's in equilibrium, we want to be using Hooke's law. We'll say the force of the spring in this direction equals the applied force in the other direction. And the problems are usually pretty straightforward. If we have a system in motion, then we use spring potential energy because we can't deal with the changing force that comes with our changing displacement. So if it's moving, we have to use spring potential energy. If it's at equilibrium, we actually could use energy equations often, but it's easier to use the equilibrium equations. So that's the big takeaways for springs. And then if it is in motion, we're going to be using, I should have written this better. Oh my goodness, I'm a mess. The spring period equation, which is this one here. So those are the big equations, the big things to keep in mind for springs. If you really want to look more at springs, just rewatch that spring facts video. For pendulums, the other piece that we want to look at is just a reminder that we have a centripetal acceleration at that lowest point. So when it's right here, whether it's going that direction or going that direction, it has an acceleration up towards the middle. So keep in mind that even though if it was at rest, it would be in equilibrium, passing through that position, it has an acceleration upwards. And then the period equation for a pendulum, just remember that exists and that it's based on the length ng. Remember that for springs, we don't care about the length of the spring, we don't care about the displacement, we don't care about the acceleration due to gravity. On pendulums, we don't care about mass. Last thing to talk about is just these graphs here that show up every once in a while. Actually, not super often, but I'd feel bad if I didn't review them one more time. This area here is the displacement of the graph. So it's either the displacement or the amplitude. And so it would be, for the spring, it would be our x value. And for the pendulum going back and forth, it would usually be some value of the, words are hard right now, some value of the change in height. And then if we're trying to figure out the period goes from a cycle that repeats. So that would be the period. And if we want to figure out the frequency, it's the inverse of the period. One last thing that I want to mention on pendulums, I should have put this in a different video, but I just remembered that I really need to kind of cover this real fast. These lengths are both L, but if I want to figure out what this change in height is, there's a trig trick that I can do. So since this is my angle and this is my hypotenuse, this distance right there would be L cosine theta. So if I want to know this distance here, the change in height, it's actually going to be L minus L cosine theta. So it would be the length here minus that length L cosine theta, or more simply, L1 minus cosine theta. So keep in mind, if you ever need to figure out the length of it based on the angle, this is how you'd go about it. So that's pretty much everything on simple harmonic motion. The formulas, big concepts. If you want to look more into springs and pendulums, again, go back to those appropriate videos. I just wanted a quick review to help you guys out. So thank you guys for watching. And this is it for this unit. Thank you.